All right. We'll continue with our discussion from last time. Okay. So looking at gradient methods. So one important thing which you understand is how do you terminate an algorithm? The algorithm by definition doesn't come with a termination criteria. To terminate gradient methods. What we have been doing is we have been running this algorithm xk plus 1 is equal to xk plus alpha k dk. This just continues for a particular choice of alpha k and dk. When should we stop? Is there a reasonable criteria we can come up with where we should stop?
So if we give a error from like xk plus 1 minus xk, will be the norm of the distance of them will be less than a small epsilon.
Okay. So one candidate. For some fixed epsilon. That's one candidate. What else can you do? And you're free to welcome to tell any problems you might associate with any of the options. What was our objective in trying to do something like this?
Usually get the slope to be.
Yeah, so could that not also give rise to a terminating criteria?
So slope eventually.
No, so give me the criteria. I'm running an algorithm. I have to, at the last line of the algorithm, I have to say stop if something. What is that if?
F of x minus 1 minus alpha x minus. Okay.
I'm allowed to compute this, right? What else can there be? And think of the associated problems with any of these methods. What could be a potential problem?
My take goes off. Okay.
Is that the only problem? Because that's the problem of the algorithm. That's not the problem of your terminating criteria. Once you fix an algorithm, that algorithm will take as much time as it was designed to be. But that's not the problem of the criteria of stopping. So the problem we're interested in is what is the problem with these stopping criteria? Is there a problem with that? Irrespective of the algorithm you're using. So among A and B, what would you prefer if you're running an algorithm? Which one would you like to pick? Provided you're allowed to compute the gradient. Why? What is the problem with A?
Like you will say that you are in some ball,
yeah,
where your points are getting your approximation getting closer and closer.
No, you're stopping as soon as this happens.
Yeah, but it doesn't. The first condition doesn't suffice that the gradient will be smaller as your intent, right?
Yeah, but what is the, so give me a precise problem with that approach. What if I were choosing criteria A to terminate my algorithm?
The first time it happens, it will terminate.
Yeah, that's the algorithm.
But like it's not necessarily the xk and xk minus 1 are not necessarily close to the x star where derivative is.
Huh.
So, I mean, if it's not close to that, then you're not at h star.
So that's terrible way of stopping it. It could be that your algorithm in between somewhere was having bad steps. You never allowed it to go to the right steps. So A definitely is not a good criteria. What about B? Are there any problem with B also?
depending on the function, even in B, like, if it's like one of those functions where the slope is naturally small at each point. Like,
But then you're okay, right? That's not really a problem.
but you have to choose an epsilon and such a.
No, epsilon is chosen ahead of time. That's your error tolerance.
Yes.
Now, if you're creating a function for which for lots of points it is small, that's okay. It's like almost as flat as you like. That's not a problem.
Whatever the problem might be, if we just choose the a square plus b square less than epsilon, like the condition 1 plus condition less than x square less than epsilon.
I don't know. We're talking about B and what is the problem associated with B. Let's not combine A or B or whatever. If B is my criteria, is there a potential problem I can face? So think of two different functions for which it will stop at different points, even though it should have stopped at the same point.
Sorry.
So think of two functions for which this criteria will stop at two different points, but it should have stopped at the same point. Think of f1 as some function f and f2 is some c scaled with respect to f, where c is some constant. What will be your stopping criteria be in this case? Suppose I run it with f1 and f2. Will it stop at the same place? So it's scale dependent. That's your problem. That's your problem with the following approach. Even though the optimizers are the same, the algorithm is going to stop at different points. So what's a simple fix to that? See, what is the problem we are interested in really? That wherever we are, we cannot really estimate how far we are from the optimum. That's essentially the problem. So it's not a simple problem to overcome. Unless you put lots of conditions like Lipschitz condition, smoothness condition, strong convexity condition, you can't really do much. But at least for this problem, can you propose a simple fix?
Like you wanted a condition from out of these where it will scale independent.
At least, yeah. So what if I just normalize it with the first starting point? So at least the scale invariance will be a property of the algorithm. So instead of just looking at the gradient at point xk, I divide it by gradient at point x0 or in fact any other point in between. But x0 is the starting point, so I could just simply start with that. So that will at least take care of this. This still will still face some issues, and because we are not imposing any conditions on f, not everything is going to go away. So in your homework, you'll see some interesting property. So this is typically what is used when you don't know much about f. If you have convexity, then you can actually estimate using convexity how far you are. So currently, we're not imposing any structure. In your homework, you will see some condition with respect to the. So something. Yeah. Something like this. So look at the gradient direction. Look at f of k d over norm of d. Depending on this quantity to be less, greater than equal to m, for some m, you can actually estimate how far you are from your optimal. So that will be an homework exercise. You'll soon see. So you need some extra information to do better than this. With convexity, you can easily see that wherever I am, I should be able to estimate how far I need to go before I can claim optimality because of the question. Problem with A? Okay, so now let's look at a nice function. So let's say this is my x star. I'm running some algorithm. Okay. Now, this is xk and this is xk plus 1. Now, suppose my algorithm somehow in bit. So for this particular case, I can't cook up a bad example right away, but just imagine that an algorithm which is running at a certain point of time made very little progress, just depending on the local behavior of that particular function. But that doesn't tell me anything about how far I am from x star. That's the problem. If you terminate just by looking at the distance between consecutive iterates, it could be that you're far away, but just because your algorithm encountered a particular function in this neighborhood, that it said, okay, for the moment, I'm only going to make very little progress. But it could be that from xk, tremendous progress is made later. That's quite possible. Sorry? Yes. So this is a problem we will face if the functions are not nice. That is, they're not convex, not smooth, not Lipschitz, all those things. If they're convex, Lipschitz, possibly, you can come up with such a criteria. Because if you know something about the curvature and it's convex, you should be able to say that this only happens if I'm close to the optimal. So those controls I don't have currently. It's only if I impose certain properties on the functions, I'll get that. So in general, it's not a good idea to do that. For certain cases, it could be. All right. So now we'll progress similar to last time. So it's essentially a theorem. And let me write the theorem first, slightly longish statement. Tries to explain why these gradient-based methods end up converging to local minimizers. So let be C1, it's differentiable. And the algorithm we are running is xk plus 1 is equal to xk plus alpha k 3k, while ensuring that f of xk plus 1 is less than equal to f of xk. So any algorithm for which this is true, the theorem will hold. So this is not specific to a particular algorithm, a particular step size choice. And assume that all limit points of xk, the sequence xk, are stationary. Moreover, assume further that there exists two constants s and c greater than 0, such that alpha k is always smaller than s and norm of decay is bounded like this, c times norm of f of x. Now let x star be a local minimum of f, and let x star be the only stationary point in some neighbor of x star. Then there exists an open set S with the optimal point belonging to S such that if some x bar belongs to S, then all further iterates belongs to S for all k greater than equal to k bar. And xk converges to sequence x star. Slightly longish statement, but slowly parse it. So look at the bottom part first. All those are technical conditions. So let's say x star is a local minimum of f. And around x star, there exists a neighborhood in which it is the only one. Then what is this being claimed is that there exists an open subset where x star belongs to that subset. And if your iterates have entered S, that is some xk bar belongs to S, then it will remain inside S thereafter, and it will converge to x star. The first part is essentially all the technical parts, that when will this happen? But the bottom part is really what is being claimed. So for that to hold, you need all those technical conditions, that alpha k remains bounded and dk also remains bounded with respect to the gradient of f of xk.
It's not like if you're talking about if x star is a local minimum, like it's a stationary part, and so then if xk is converging to x star, then there will be an open set around x star, which will.
But where is the guarantee that it converges? That's the whole point.
So to prove, yeah.
It's saying both. It's saying once I enter S, I remain within S and I converge to X star. So essentially what you're trying to say is that once you get close to a local minimizer, these don't jump around. These algorithms of that type, they don't jump around. Once they're close, they remain close and converge. Unless they get close, you don't have a guarantee. So it's not saying that for every possible trajectory, it will actually enter there.
If it
enters there, then it remains there. That's all. Okay. And these, why we are making these strong or difficult assumptions for us is that we are not imposing any structure on F. From next class onwards, we will look only at algorithms and their guarantees for convex functions.
So I was thinking about a function
that
is for the 1 by x sin x.
Yeah.
Like for x positive.
Yeah.
So it will slower. So if we take the peak points only, the interest conditions is fine, but not the same. The second condition mentioned that we have to be in a particular neighbor of the peak points, basically.
Okay.
But if we choose a function that x sin x near to 0, so the oscillation will be higher there, right?
So,
and around 0, we cannot get any open set, but the iteration will be converging to that 0 point, right?
Let's see the proof. Hopefully, you will get convinced that this better be true. So the example you chosen for yourself is very complicated. That's why I'm hesitate to actually start working on it.
So we are looking for the peak point, like we are
peak point. What is your function, by the way? F of x is
X sin x.
okay. What does it look like? Tell me, what does it look like?
Next over the multiples.
It goes to 1 or more than 1?
Like draw x like y constant and then draw sin.
The amplitude will be higher and higher.
This is my y equal to x line. What do you want? You want this? Is that what you're saying?
No, that is x plus sin x.
Hmm.
What is the maximum amplitude? This keeps increasing, right? That is clear.
Yes.
Okay. So
It will just the period it will be increased.
but why is it not unbounded?
No, you have to choose 1 by x. Then it will be so much oscillation that I want to.
But why doesn't it go to minus infinity?
Because are you restricting your domain to 0?
For the moment is unconstrained.
Okay.
Okay. You're not looking at constraint optimization. And by definition, you're not assuming that functions are, the optimizers are not unbound. So it's not going to minus infinity. Okay, so my hypothesis H star is a local min with no other stationary points nearby. So therefore, there exists a row greater than 0 with f of x star being less than f of x for all x such that x minus x star is less than equal to rho. That's just by the hypothesis that I'm like x star is the only local minimizer in a small neighborhood. So there exists a row of this type. And F has no other stationary point in this set. That's just by my hypothesis. Now we're going to define a new function, which is going to be P of t is minimize f of x minus f of x star within this ball, but which is somewhat slightly strange. Minimize over x such that x minus x star is less than equal to rho. So I'm within this, but greater than equal to t. Make sense? So what is the picture? Picture is here is some x star. Here is our set of this type with radius rho. And then I'm drawing another annuli with P. And I'm looking at in this domain is what this minimization is over. So f of x minus f of x star in this domain. Okay, so what do we know about fx del fx star? This is 0 by definition of the local min And because of the continuity, this is continuous. So what can you say about around x star? This is so around x star, del fx essentially is small or arbitrarily small as much as I want. Or x close to x star, since f belongs to C1, right? So what I'm going to choose, I'm going to choose an epsilon given this row such that the following happens. So let me write it here so that at least the picture will be clear. So I want to show, given an epsilon belonging to 0 to row, 0 is open. Given this, choose r less than epsilon such that what happens? X minus x star is less than r implies x minus x star plus s times c times norm of f of x is less than epsilon. So this is r. What am I doing? Fix the epsilon between 0 and rho. I want to choose an r less than epsilon such that whenever x minus x star is less than r, it implies that x minus x star plus these two constants multiplied with the gradient is always less than epsilon. And why is this true? Because of that. Can somebody convince me?
So x minus x star is always less than the modulus of x minus x star is always less than rho. It will do that at the time. So you're asking us to prove that there exists such an R. It proves that.
So I'm choosing, I'm claiming, question is, why does such a choice exist? So I'm choosing r less than epsilon such that whenever x minus x star is less than r, the implication holds. I at least have to convince that it is not a vacuous statement. I can always do that. Question is, why can I do that?
So the value of del fx, it's on your hand because you know that if del f star is 0.
Right. So as I go close to x star, there always exists x such that del fx norm is as small as I like. So the second term, I can make it as small as I like, and x minus x star is less than r. R is less than epsilon, so there is always room between r and epsilon. So I can always squeeze that much inside. So I can make this choice of x. So this actually holds. So one step at a time. So all we are trying to establish first is that if an iterate xk belongs, so we'll also define that open subset because the theorem claimed that there exists an open subset. So I will describe an open subset and then say if some iterate has landed in S, the next iterate will also remain in S. That's what we're trying to show. That convergence will come after that. So now comes the definition of the open set. To define the open set S, S is X such that X minus X star is less than epsilon and f of x is less than f of x star plus phi of r, where r was defined in the previous. So that's the slack I'm defining for us. I'm in like in distance from x star, I'm at most epsilon. in distance in terms of f, I'm at most phi of r. So why is this? So claim s is not equal to phi. So okay, this is an empty set phi. We have to put a double thing because I used phi of r there. So this is empty set. So why is this not an empty set?
Because
Mhm.
you define phi of t to be the min, right? Min of x.
Yes.
So certainly it must exist, right?
So just claim, give me a membership. So he's saying x star exists. Anything more than x star exists? So claim, he making a claim that x star belongs to S.
Right.
What about something more than that? That definition only requires this definition, phi of t. Doesn't require anything more. I'm planting phi of r. What is that phi of r? Phi of r is such that if you're close to x star, then you're also close in terms of something to do with s times c times del f of fx. So can you give me one more point than x star which belongs to S?
So, the main part is to consider the second condition, that is f of x less than
Yeah,
x star
that's correct.
plus phi of something.
Yeah, so this is trivial, right? Because all points which are at distance are there.
So,
Question is, what kind of points are lying in here?
so from the inequality that you have written in the last code,
Yes.
the second one, yes. So we can choose a point corresponding to choosing a rho and gamma.
Mhm.
We can choose a x star, x satisfying that condition. Then obviously the phi for that point, the phi will satisfy.
Phi will satisfy what?
That
Phi of t is what?
like the value of phi of t is less equals to minimum of fx minus fx star.
Yes.
So for any other value point in that ball, it will be less equals to phi of t less equals to fx minus fx star.
Okay.
And you can multiply by minus and you can just make that. Means you can,
Can you say this simply? It's not that complicated.
Take an x such that it's such that take an x such that x minus x star is less than r.
Okay, that's epsilon. So epsilon is larger than r. So it's automatically less than r. Okay. No, it could be in between r and, but okay, fine. I'm giving you more slack here, right? R is only smaller than epsilon. So this is not important. What is important is this.
If we choose x such that x minus x star is less than r,
Okay, choose.
so then the definition of phi of t is the,
Yes,
so
I'm here.
yes,
You
so
can use
phi
what?
of r is just going to be the minimum of this.
Correct.
So phi of r will just be less than or equal to f of x minus f of x star.
Phi of r. Sorry. P of r.
Will be less than or equal to, because it's the minimum, right? Phi of r is
But what is the definition of phi of r?
on the annular.
yeah, on that on
Is equal to min of x, f of x minus f of x star,
The region
x minus x star between what and what?
between r and rho.
Rho. Okay. So now tell me what you want phi of r to be.
So that phi of r, it chosen x to be such that x minus x star is
so if you choose x minus x star below r,
Below r.
yes.
Okay. So
Inside the
mhm.
then the equality that you will get an inequality, that is PR data equals to fx minus fx star. For any x at this time, that
For any x what? For all.
any x such that x minus x star less than r.
Okay. Why is that true?
rho. It's all it's really good.
So the equality was satisfied because
But look at the second condition defining S. Interpret it in terms of phi of R directly. Don't try to do this. If you take f of x star to the left hand side, what is it saying? That f of x minus f of x star.
It's less than P.
Yeah. What is that in the language of things we have set up for ourselves?
So P of R is the minimum value. Right?
Okay.
But we're saying that f of x minus f of x star will be less than the minimum value of R.
Okay. So what's going on?
So then x cannot lie inside that. X cannot be inside R less than or equal to x minus x star. Because if it is less, if f of x minus f of x star is less than P of R, but P of R is already the minimum over that set. So if x lay inside that set, then it would be the minimum. But so that's not the minimum. So
Okay.
that x must lie outside. So it must lie in that inside x minus x star.
Okay. What is the final conclusion?
So take an x such that x minus x star modulus is less than R. It would,
Okay. And why? Are you convinced?
I just say it again.
Just try to subtract it out. So if you take fx star to the left hand side, what happens? It's saying find a point x such that f of x minus f of x star is less than phi of r. Does there exist an x? Does x star satisfy that, first of all? Does x star satisfy f of x minus f of x star to be greater than phi of r? See, phi of r by definition is greater than or equal to 0. So,
P of R is greater than six, so it's
there is a strict inequality there. So first try to establish that x star satisfies that condition. And then we can pass it all to the continuity of f so that there are many points around f for which it will also be true. So why does x star satisfy that?
because we have given that the x star is the only local minimum.
In the neighborhood, yes, yes. So say something.
Yeah, so basically there is no other point which will
See, within this neighborhood row, the x star is the only minimizer. So it's strict. So x star definitely satisfies that. The rest of it is all continuity of f. Is it still clear? But x star definitely satisfies that equation. And rest of it is just the fact that f is continuous. They will always be able to find small enough. Rest is jargon. You just write it appropriately. You convinced? So x star belongs to S, and since f is C1, S is not equal to 5.
can you just tell me, can you plan another point?
What are 5?
You want to get that?
Just get small enough, that's all. You can always write that circus there. You can go back home and do it. Okay, so now the claim really is that if xk belongs to S, then xk plus 1 belongs to S. That's what we want to do. So this phi of R will keep coming. So now I'm replacing R with xk minus x star, which is nothing but min of x minus f of x star x such that x minus That's my definition. Is x equal to x star? Sorry, not x. Xk a feasible solution to this problem? I'm not saying optimal, feasible. So x equal to xk star will be feasible, right? Because this will essentially be, this will disappear and you'll only get less than epsilon. Okay. So P of star is less than equal to f of xk minus f of x star, because the min will only be smaller, and this is less than P of r. Hence, is this okay? Why is that true? So R has been used to even define S. Okay. Because xk belongs to S. By definition, what is the definition of S? So by definition, what is S? All points x such that f of x less than f of x star is less than P of R. And the fact that xk belongs to S just tells us trivially that that is less than equal to phi of R. So that's just by the definition of S. Okay. Now, somehow I want to claim that xk plus 1 belongs to S. What is xk plus 1? Really think about it. That's nothing but xk plus alpha k times dk. So what do you think we need to show that that also belongs to S?
So we also have bound on alpha k and dk.
Yes. Alpha k is at most S and dk norm is at most
By some
C times gradient of f of x. So somehow I want to show that xk plus 1 also satisfies the two conditions of S.
So we can prove it using that condition, right? Like x minus x star plus sc that type of x
Is less than equal to epsilon. But for points which belong to less than R. So there is one step required here. Somehow I have to make sure that xk minus x star is at most R. Why do I get it from here? So the last inequality I claim gives you that xk minus x star distance is at most R. Why is that?
So let's say it's not. Let's say it's not.
Why do you want to go there? It's one way of doing it, but might complicate matters.
Because phi of r is defined as the minimum of x such that r is less than or equal to x minus x star is less than or equal to rho
Yeah,
f of x minus f of x star.
yeah.
But so when x cannot, if f of xk minus f of x star is less than p of r, then xk cannot lie inside that set. So it has to lie outside that set, so xk will be less than. But xk will not xk will be inside too.
So let's call this inequality 1. So claim is 1 implies that xk minus x star is less than r. Is there a simple answer to this? Once I have this, then I can use my setup, which says that for all choices of xk minus x star less than r, x minus x star plus sc times the gradient is at most epsilon. But why does one imply this?
Is that
Maybe something similar. It's like you're saying too many things, and I don't think the rest of the class follows. So that's why I'm trying to asking you to do it somewhat simply. So what does it even mean? So recollect.
If I just tell you that for any r prime less than r, phi of r less than phi of r prime less than phi of r.
This is the definition. What are you saying? Phi of r
Prime less than phi of r for all r prime less than 1.
This is true. R is decreasing r. So the minimum can only go down. Right? So minimum has gone down. Fine. Okay. Appears correct. So
Yeah, so
is that all?
so the r prime is basically
Just look at this. Phi of
x is taken from the set S.
yeah.
Uh,
Xk is from S, yes.
x is from
And x star also belongs to
yeah.
S.
So the distance of x star minus x is something r prime of the form.
Okay. Mm-hmm. I don't know what he's saying. So you're saying xk minus x star is how much?
Is on r prime.
Okay.
That is less than r.
Why? That's what you'll establish. Why is it less than r?
We know that fact that
Which
for the
Above thing is we know. Here you're saying is r prime less than r. R has been used to define S. So why is it r prime? Because it belongs to S. Is that what you claim? What do you know? Xk belongs to S. Is that why you're saying that
yes, like
r prime is less than equal to r?
x star is also in S, xk is in S.
X star is not important.
Yeah, so it's
So look at the definition of S. It's all points which are at most epsilon from x star. We know that xk belongs to S. So that means that xk minus x star is less than equal to epsilon. And also this. Okay, from there, how do you get this? That xk minus x star is less than equal to r prime, which is less than equal to r. What have I shown so far? I've shown this. F of xk minus f of x star is less than phi of r. Why does this imply this? And xk belongs to S, that much we know.
xk minus x star.
Let's compare the first leftmost and the rightmost. In between was just an artifact of the definition of xk belongs to x. So what is the leftmost? It's phi of xk minus x star. Rightmost is giving you less than phi of r. Already shown that if one increases, the other decreases. So it automatically gives you. So keep track of what is going on. Things are much simpler than what it appears. So it's in fact 2 and 1. Okay. So now, because of this, I know from earlier thing that xk minus x star plus s times c times gradient of f of xk is less than equal to epsilon. That much I know. Now I'll go to xk plus 1. What is xk plus 1 minus x star? Is equal to xk plus alpha k dk minus x star is at most just by triangle inequality xk minus x star plus norm of alpha k. And this is at most sorry,
R plus
this is at most s times c times
delta f.
yeah, and that is what I just bounded. So this is as it is xk minus x star plus s times c times norm of del f of xk. And this is at most epsilon. Okay, so now what has happened? What membership I can establish about xk plus 1? That this is true for xk plus 1. What about this? I want to prove that xk plus 1 belongs to S, so I have to put both conditions. So no work is needed. All I have to say is this, and that's the reason. See, xk belongs to S. That much we know by hypothesis. What is f of xk compared to f of xk plus 1? By definition, it's a descent direction. So f of xk plus 1 is how much? Compared to f of xk, at most f of xk. Because that's the hypothetical theorem that for algorithms which are in descent directions, something falls. So for f of xk, we know that f of xk is less than f of x star plus phi of r. F of xk plus 1 is just simply less than f of xk. So the second condition also holds. By definition, f of xk is less than f of x star plus phi of r. And by hypothesis, f of xk plus 1 is less than or equal to f of xk. Therefore, A and B together imply that xk plus 1 also belongs to S. So all the hard part is over. Now all you have to show is that xk also converges to x star. Can you give me one line argument to that? No more math needed really. And the hint is to think of, you had this set S, which is open. Look at the closure. So let's call S bar to be the closure of S. Can you make an argument just using this?
Like a bounded, like we have a infinite many points in a closed bounded state.
Okay.
It must have a limit.
Okay. Carry on.
So xk that equals like
You have to use all the hypotheses of the theorem. Theorem said lots of things.
so x,
All limit points are stationary points.
yeah, x,
This neighborhood only had one, so it better converge. So all those things you have to put together.
yeah.
Okay.
So after a tail of the sequence xk is false in a part.
Okay.
This one is closed and bounded.
Yes.
So the sequence xk must have a subsequential limit. Suppose xnk, xkn.
Fine.
So xk converted to some point x tilde
Yes.
in case. And
Now use all the theorem's hypotheses
yes,
that all limit points are stationary, and in the neighborhood S there is only one. So it better converge to the X star. That's all. If you want me to write, I'll write, but that's essentially what it is. So S is a set defined, S hat is the closure of S by hypothesis. All limit points of xk are stationary. 1. S hat is compact and xk, the whole sequence, once it becomes part of S, it remains within S. Therefore, the limit of xk is at least one limit point in S bar. But X star is the only one in S. By our choice of the open set. What have we done? We looked at the neighborhood where X star is the only stationary point. So this implies that xk bar, or yeah, the limit of xk.
I would say you're saying that xk converges to some limit point in the closure. But then you're saying that x star is the only limit point inside the open set, right?
Yes.
But we've not, like, in the sense that it could converge to some point in the boundary, right?
Okay. How will you avoid that? That's the question. Because what have we shown? That xk always remains within S. So it never goes outside.
Yes, but so its limit could be on, is it not possible to the limit to be on the boundary?
Think. Why did we take the closure is the question.
Because the closure is closed, right?
Yes, correct. So what did I gain by doing that?
Because then we could take a subsequence of the which would
Yes.
converge to
so your limit point might be lie on the boundary of the
Fine.
point, right?
Fine.
But the algorithm that you have run, you have seen that the value of the xk will be smaller equal to with the previous iteration.
Okay.
And
that's in terms of f, not in terms of x.
Yeah, in terms of it.
Yeah.
Nobody is saying that firstly that it will converge to x star.
We are saying that.
Yeah, but apparently in that argument it is not.
Okay.
Like in the limiting argument, like where the substitution limit that might not be x star, it might be some x tilde in within S. But we are claiming that x tilde and x star are exactly the same point because we have only one optimal minimizer.
Yeah.
Local minima in that set S.
I don't know. I don't follow you. So what's the difficult? What's really the problem? Think about it. What remains? If at all there is a gap, what is the gap?
So what happens like in the sense that how do you ensure that X does not convert to fault on the boundary?
Okay. But what is X star with respect to that? What did we ask for X star?
X star is the only point inside S which carries.
That's all we know.
Yeah.
Okay.
So if the thing is that if Xk is converging to some point in S, it must converge to X star only.
Yes.
But I'm saying that what if it converges to some point of the boundary? Like
Yeah, so-
that it doesn't converge.
Right. So how do you preclude that is the question.
Yeah.
Think about
X is also C1, right?
Yeah.
First, right? So basically, my idea is that just to in the if he's asking that in the boundary point, it might happen that if you include the X boundary of S, then the uniqueness of the X star might drop.
He's not asking for that. He's asking for something else.
I'm just saying that like
No, it's valid point. I'm just saying, can you convince yourself that no, that cannot happen?
I don't know how to convert it. Right?
For it to converge outside, what has to happen? For it to converge outside, what has to happen?
For every point in the boundary, there would have to be an epsilon neighborhood containing infinitely.
Correct.
Well,
I think it's a good exercise. So go home and work it out. I think it'll clear up certain things. So let me write it clearly as at least one. Okay. All limit points of X has at least one limit point of R. X is the only one in S that is stationary. Thus, for some xk, once I get into S and xk plus 1 belonging to S implies the convergence. That's what I want to say. Implies the result is what that means. It's a good exercise. Just try to convince yourself that cannot happen. Okay, so let's try to do something interesting. Is the big picture clear what we did? There are lots of technical conditions here in the theorem. This is the real part, that if your iterates have essentially gotten into a small open set, there exists an open set where once the iterates enter there, the iterates remain there and they converge inside the local minima over there. That's what really is. These are all technical conditions required. Okay, so let's now finally look at speed of convergence. All right. Great. So we have this typically an arbitrary function f of x. Suppose I were to look at so I can write f of x as around x star to be del f x star x minus x star plus of x minus x star transpose del f square x minus x star and plus something, right? This term is essentially 0 by the definition of being x star. So it's actually sufficient to look at the quadratic term for understanding the rate of convergence, really. Because f of x star is just a simple shift, whatever that fixed number is. All you're really interested in is how it's behaving quadratically. And in particular, we can look at f of x to be half x transpose qx. I'm just substituting x for x minus x star. Q is nothing but the Hessian. People with me that I can do this? So now this is the simplest function you can handle. We will try to understand how our algorithms actually converge for the quadratic function. So let's start with steepest descent. What is the algorithm? Xk plus 1 equal to xk minus alpha k. Right? So what is gradient of f of xk? Remember, f of xk is, just write it again. F of xk is half xk transpose q xk. So what is gradient of f of xk? Anyone? Q times
X.
So what does the update look like? Xk plus 1, xk minus alpha k, xk. We can take xk common, and I get essentially I minus okay q. And where is xk converging to? We just look at this problem. What is the optimal solution? Q is positive definite, let's say. You don't have to look anywhere. It's just a trivial answer I'm looking for.
0.
Yeah, so xk is just going to 0. So typically what do? We look at the speed of convergence as xk plus 1 minus x star over xk minus x star. Here x star is 0, so all I can do is just look at xk plus 1 over xk. That is nothing but I minus alpha k q. Okay, so now have you guys looked at eigenvalues of these type of matrix? I is identity, alpha k is a constant, q is
Positive.
some positive semi-definite or positive definite matrix. So what are the eigenvalues of? And let's look at the square of this. Just yeah.
This is like we're taking a norm of what is like. So the determinant.
This won't be the determinant.
Determinant.
This won't be the determinant. What will it be?
Okay, like the norm, right? Yeah. We're taking the norm of that.
Yeah. So what kind of matrix this is?
Nilpotent.
Nilpotent. And take Q to be. Q is PD. Let's say. Positive definite. Positive definite. It's a symmetric matrix.
Q is positive determinants.
Yes. Okay. I won't ask you to prove it. Symmetric. And so is alpha q square. This should also be symmetric. Okay, symmetric, A square is symmetric. Okay. What are the eigenvalues of this matrix after the square? And is this positive semi-definite?
The whole matrix.
Yeah, I minus alpha q whole square. Is this positive semi-definite? What's the test? Whether x transpose I minus alpha q whole square x greater than equal to 0. That's my test. But what is this quantity equal to?
It's just the norm, like that square. X times, yeah.
And this better be equal to 0, greater than equal to 0. So this is equality. So this is also PSD. What about the eigenvalues of I minus alpha q whole square? You know a lot about q being positive definite.
Eigenvalues are real and bounded by the maximum eigenvalue bounded by 1.
No, in terms of the eigenvalues of q. That's what we want. So what are we interested in? I minus alpha q. That's the matrix we're interested in. I can write q as I minus alpha u d v. Or u du. That's important. Can I do this as u du or u dv? I can do u du Hermitian. Right? It's something stronger.
Yeah, because it's symmetric. Yeah.
It's important that I am allowed to do u du Hermitian. And then what can I do? I can write u I minus alpha d u Hermitian. Same thing. Now, what kind of matrix is this? The inside one? It's a diagonal matrix because I is diagonal, alpha is a scalar. So what are the eigenvalues of this matrix? This is again the eigenvalue decomposition where u's are the vectors. These are the eigenvalues. What are the eigenvalues? I minus alpha d. So I of I minus alpha q is nothing but the set 1 minus alpha lambda I going from let's say n lambda I r. So what are the eigenvalues of I minus alpha q whole square? Are essentially 1 minus alpha lambda I square. Okay, so what did we want? We really wanted to say something about xk transpose I minus alpha q whole square xk to be less than something. What is that something?
Maximum.
So now maximum is with respect to lambda max or lambda min? That's the interesting question.
We are taking the maximum eigenvalue of this of I minus alpha q square.
Yeah, so
Lambda I should
among all possible choices, which ones will be the max?
lambda I would have to be minimum.
But depending on how these are, either you will get the min or you will get the max. This will be at most max of 1 minus alpha lambda min, comma, 1 minus alpha So what have we got for ourselves? That xk plus 1 over norm of it less than equal to this quantity essentially. Max of removing the squares 1 minus alpha lambda min. Now, what alpha should you choose? That's the question. You would like this quantity to be as small as life, right? So essentially, you will pick alpha such that you equalize them. You don't want any of them to be dominating. So, what is the choice of alpha which will equalize them? So, you don't want one of the two to dominate. So, you'll pick an alpha such that both of them are equal. Because the one which is larger will kill your convergence rate. You want this quantity to be as small as possible. So, you just equate. So, 1 minus alpha lambda min equal to 1 minus alpha lambda max. And what you end up getting is alpha is equal to how much? 2 over lambda min plus lambda max. And the result is that final answer you get is the convergence rate is lambda max minus lambda min over lambda max plus lambda. That's your final. It's a linear convergence with this particular rate. Is it good news or bad news? Sorry, it will converge, but
Not faster, linear is like.
no, but what does it tell you? If lambda max and lambda min are very close to each other, what's happening?
Very close to zero.
It's very good, right? So you want the matrix Q to be such that they're very tightly, so all the eigenvalues are very close to each other. But what if it's not? One is very large, other is very small. No, so it can't be more than one, right? Can it be? No, it can't be more than one. But it can go very close to one when lambda min is very small. So you don't want ill-conditioned Qs. So Qs having eigenvalues greater than zero but very close to zero is what you don't want. And that could possibly happen in particular instances. So what's a fix you can insist on, which will try to get these lambda max to lambda min close to each other? So this is not necessary always that lambda max is close to lambda min. But is there a way to massage your algorithm in such a way that the resulting lambda max and resulting lambda min are close to each other? So the fix you have to do is to the algorithm. If you've seen something like if there is a random vector which has a non-trivial, what is it called? Covariance matrix. What do you do to make it independent? All of you have seen this. So take a vector whose covariance matrix is not identity or scaled identity. What operation can you do to that vector so that the resulting covariance matrix is identity? It's called something. If you've not seen, go home and do this exercise. Take a random vector with non-trivial covariance matrix. You're allowed to do something to your random vector so that the resulting covariance matrix should be identity. And assume that the covariance matrix of the random vector is positive definite. Not seen this. So take a random vector x. This is completely aside, okay? With covariance matrix, let's say Q. Okay? And Q is PD. A new vector y, which is, let's say, Q minus half x. What covariance matrix will y have? Identity?
Yeah, because then
So this is called so this is called whitening. Not seen this?
seen it, but we didn't know like this is the thing in law.
Oh, this is very, very useful. It's called, so this is called color and this is called white. So that's all. So something very similar is what, see here, what really was the problem, that the maximum eigenvalue and the minimum eigenvalue are very different. If you whiten it, the both of them will become one. That's exactly what we're going to do here. So instead of looking at an algorithm, what was our algorithm? Xk plus 1 equal to xk plus alpha k, or rather, the algorithm was minus here. Minus alpha k del of xk. All we're going to change is xk minus alpha k dk, or rather d, it doesn't matter, of xk, where dk is nothing but q to the power minus half. That is all we will do. And magically, you'll get the resulting lambda max and lambda min to be equal. That's what will essentially follow. So we will see why that will be true. So let's start. So let's say S is equal to dk to the power of 1/2. So my algorithm is this. For the steepest descent used dk equal to identity. Instead, let's play it with dk. Let's call dk to the power half to be equal to S. What was my original problem? Original problem was f of x. I'm minimizing this, which is x transpose qx 1/2. Let x is equal to sy. I'm doing the transformation. So now the equivalent problem is h of y to be equal to 1/2 y transpose s q and s transpose s, yeah, s, it doesn't matter, sy. So this should be s transpose. So what will be my steepest descent step here? Yk plus 1 in terms of y, yk minus alpha k times del of h of yk, right? I'm just going to multiply S to all of this. Okay. Does anybody see what's going on? What is S? This thing from here? Recall the formulation. This I can write this as xk plus 1. This I can write as xk minus alpha k. What is this term? S into S Q yk, right? This is the gradient of this is SQy. So what has happened? Earlier I was taking xk plus 1 is equal to xk minus alpha k times the gradient of f, which was simply q times x. Now I got s square qy. And what is s square? I chose s to be equal to d to the power half. So this is nothing but simply d. So this is xk minus alpha k d times qyk, which is nothing but, now qyk is what? There was one s missing here, sorry. It should be another s so that I can make this.
Qy is qx.
Sorry.
Qx.
USYK is.
Okay. So it will be q qxk, and this is nothing but the gradient of f. Give me one second. Xk minus alpha k gradient of, yeah, question.
D type.
D should be there, yes.
Yes.
So what has happened? Something strange is happening. So this should not change the problem, right? Just making the S is equal to SY transformation, S being positive definite. Nothing should really happen. Okay. So what is really the punchline? My iterates are now no longer xk plus 1 is equal to xk minus alpha k gradient, but this inserted matrix D. So what can I do with this? Why did I do all this circus? What have I achieved doing this?
Define D to be equal to.
What do you do?
Define S to be equal to B by half. What did we define B as?
Your choice. That's the whole point. But think what is the right choice? So in the Y domain, what will be the convergence rate be controlled by? Lambda max and lambda min of what matrix? Sorry? SQS. Just look at H of Y.
S transpose.
Yeah, S transpose QS. That's the matrix you have. Now, what control do I have over this matrix via D?
Use S.
Effectively, by choosing D, I'm choosing S. Q was a matrix given to me. What have I done? I have transformed this problem to look at a new matrix, which is S transpose QS. And those eigenvalues, the max and the min of that matrix now matter. Now, can I make those max and min as close to equal as possible by choosing appropriate S? And what would be that S be? All I wanted to do is to make S transpose QS equal to identity. That's my best guess, really.
The pseudo.
Q is positive definite. Think of it as invertible if you want. If I choose S to be Q to the power minus half, what am I going to get? It's a new matrix, which is Q to the minus half times Q to the power minus half. And this matrix is eigenvalues of what?
That would just become identity.
So by preconditioning, same as all I said was whitening, essentially, you can actually remove all the trouble you have when the lambda max and lambda min are far away. So it's all just preconditioning. Essentially, rather than solving this half x transpose qx, either you transform the problem like this or you change the algorithm like this. Both of them are equivalent. So rather than solving x transpose qx, you solve for y transpose sqs, where S is this matrix. Or you try to run this algorithm where D is nothing but.
So I just wanted to mention, so the function is not changing, but the iteration is going faster and faster. Like it is
Not iteration. The ill-conditioned matrix has been now made well-conditioned. That's all.
We're making a convergence rate small.
Essentially close to zero. That's what we're doing. Earlier, the problem is that lambda max and lambda min could be very far away. But given that it's PD, I can do all this because of the minus half existence of the power of minus of. If that doesn't exist, then you're in trouble. Then you can't do much. It's just because that helps you, you can handle this. All right, let's stop here.